Hi, and welcome to a review of the Part B-2 June 2023 Chemistry Regents exam. If you haven't gone over Part A or Part B-1, they are in separate videos. Check them out. And by the time you watch this, Part C might already be published. Here we're looking at short answer questions. We're starting with question 51, and we are going all the way to question 65. These are short answer questions that you'll answer in a booklet when you take tests. The first 50 questions are all multiple choice, and then this is part of 35 short answer questions. Let's get started. I just want to note that you're going to see these lines here that separate a set of questions from another, and there's always usually in this part some information that goes along with the questions or statements. Sometimes it's helpful, sometimes it's not, but just realize it's there. All right, in this case, we're talking about the element technetium that has several isotopes. The bright line spectrum of this element has been observed in the spectra of some of our stars. Question 51. Compare the energy of an electron in the first shell of this atom to the energy in the third shell. Well, as it turns out, for any atom, as the electrons fill up that atom, the electrons that are further away from the nucleus, in the case of 51, the third shell, are higher in energy than any electrons closer to the nucleus, in this case the first shell. So the energy in the third shell for the electrons is greater than the energy in the first shell. For 52, in terms of protons and neutrons, why the various nuclides of technetium are isotopes of each other. Well, here you go with vocabulary words again. Real simple. This is a vocabulary word. This is key. It already showed up on this test. They have same number of protons, different number of neutrons. Let's keep going. 53 and 54, we have information here of a gas in a sealed rigid container with a movable piston. We have a volume of 0.250 liters at STP. Now remember, STP means standard temperature and pressure. It is on the reference tables. And we're going to pull information off there for 53. Show a numerical setup for calculating the volume of this sample of a gas at 298 K and 1 atm. We need the combined gas law also to do this, and let's set it up. Reference table A gives us our values for STP. When it comes to temperature, no matter what, for gas law questions, temperature always has to be in Kelvin. For pressure, you're going to use either kPa or 1 atm, depending on the units for the other parameters. In this question, it was atm, so we want to stick with atm. You want to make sure that you're consistent on both sides of the equal sign. Here on reference table T, I just also wanted to point out the combined gas law is the equation that we're working with. Let's get back to the question. What I did already, I took the equation and I wrote it down again. I have my initial conditions and then my final. For the initial conditions, that came from the statement here. The 1 atm is standard pressure, 0.25 liters is given in the statement, 273 is standard temperature, and then what's really only changing is the temperature, right? It's 298 K and 1 atm, but I put it in there anyway. This would be an example of a numerical setup. Now they say numerical, so you do not have to put the units for the values, just the numbers. And you're not solving for anything. That's it. That's your answer. All right, let's go to 54. State a change in pressure that will cause the gas in the cylinder to behave more like an ideal gas. Any gas is a real gas. There is no such thing as an ideal gas. An ideal gas is a simplification of the behavior of real gases, and we use this in calculations, and actually it does a fairly good job. Any real gas is going to behave most like an ideal gas at high temperature and low pressure. So that's exactly what we want to say. So we want to lower the pressure. That's all you got to do. On to 55. For this set of questions, we have a lab setup. Everything is labeled for us, and we also have a data table. We're told that the beaker contains 120 grams of water, and let's take a look at the questions now. 55, state the direction of heat flow between the candle flame and the beaker of water during the time the candle is lit. Well, heat always flows from hot to cold, no matter what. And take a look at the temperatures, right? Because we can't just assume that the water was lower in temperature, but you can see that it was only 23 degrees and went up to 86. So obviously the heat flow is going from the candle flame to the beaker of water. For 56, show a numerical setup for calculating the amount of heat in joules absorbed by the water in the beaker as a result of the burning candle. Well, for this, we need a heat equation. We do have a change of temperature with the water. Let me just show you where it is on reference table T, and we'll come back and set it up. Reference table T. We have three equations. Which one do we use? Well, it's going to be the top one. The Q is equal to MC delta T. That is the equation because water is changing in temperature. The second and third equation are for phase changes for water, when it melts or freezes, or when it boils or condenses. You got to fit it based on what you're given in the problem. Now, this capital C, which is specific heat capacity, that is going to be found on the front of the reference table for water. So let's go find that. All right, it's reference table B, and you see the specific heat capacity for water as 4.18. The numerical setup is here on the right. I always write down the equation. I would recommend that only so that you're plugging things in where they belong. You have an M, which is the mass of water at 120 grams. 4.18 is our specific heat capacity, and then it is 86 minus 23, right? It's delta T, the change in temperature. For 57, it says state how the molecular motion of water molecules in the beaker changes as the temperature increases. Temperature is defined as a measure of the average kinetic energy of, in this case, the molecules of water. What we're talking about here is as the temperature goes up, the motion increases, right? They speed up. Now we're up to 58 through 60. We have a system at equilibrium. We're told it's at equilibrium, meaning you have a reaction going in the forward and reverse direction. 58, compare the rate of the forward reaction to the rate of the reverse when the system is at equilibrium. At equilibrium, the rates are equal. It's a fact, know it. 59, state how the equilibrium shifts when the pressure on the system is increased at constant temperature. Well, in order to know how pressure affects this equilibrium, first of all, we have to have substances in the gas phase, which we do. Then we're looking at moles of gas. On the left-hand side, we have 2 moles of gas, and on the right-hand side, we have 1 mole of gas. If we increase the pressure, the equilibrium wants to favor the side with less moles, which means that it's going to shift to the right. So that's exactly what we would say. It's going to shift to the right when the pressure is increased. For question 60, compare the entropy of a sample of the dinitrogen tetraoxide gas at 1 atm to this same substance as a liquid, now at 25 degrees Celsius and 1 atm. Well, anytime that you have a gas versus a liquid, you have a higher entropy, right? More disorder, more randomness. The particles, in this case molecules, are freer to move. So the entropy of the gas is greater than the entropy of the liquid. For 61 through 63, we're looking at this reaction here of copper as a solid with silver nitrate, and then we get silver and copper nitrate solution. 61, state the change in oxidation state of the copper. If you didn't know copper was Cu, you could take a look at reference table S. And what you notice is it starts out as a solid. It is not bonded to any other element on the periodic table. That means it gets an oxidation number of 0. Now, when it is with other elements, though, copper can, just like any other metal, lose electrons. In this case, we're talking about copper with an oxidation number of +2. Now, how did I know that? Well, I have to use the nitrate and the charge for the nitrate, which is a polyatomic ion, and if you don't know the charge, go to the reference tables, but it happens to have a -1 charge. There are 2 nitrates, that makes that -2, and when I have a compound, all of my oxidation numbers have to add up to 0. That makes copper +2. So the answer here was from 0 to +2. 62, based on table J, state why copper reacts spontaneously with the silver ions. Let's go to reference table J. This table gives us a list of metals in that type of situation with single replacement reactions, and when we're dealing with voltaic cells, which metal is the most active down to the least active. The higher the metal on this table, the more active, meaning the more reactive it is, in its atom form and wants to lose electrons. So remember, your metals all are your losers of electrons, and if we were comparing any of the halogens, the nonmetals are the takers of electrons. If I scroll down, I have copper above silver on this table. What that tells me is that copper wants to lose its valence electrons more to silver, and that means silver has to take them. Since we are answering the question based on table J, all you have to say is that copper is higher on the table versus silver, or Ag+. For 63, write a balanced half-reaction equation to represent the reduction of the silver ions to silver atoms. You got a little hint there from the Ag+ from 62, and if we take a look at the equation, silver nitrate Ag is a +1, so all we would do is write Ag+. It's going to be Ag as an atom, which has a oxidation number of 0. Now, when the oxidation number is becoming more positive, we have reduction, which is the gain of electrons, and silver is gaining electron. So we would put in the +E-. There's your half reaction for 63. All right, 2 more questions here. During a lab activity, we have 15 mils of HCl is exactly neutralized by 18.2 milliliters of 0.11 molar sodium hydroxide. During the laboratory activity, and appropriate safety equipment is used and safety procedures are followed. If you didn't recognize that HCl is an acid and NaOH is a base, you could go to the reference tables. There is a list of common acids and common bases. And the key to know you're in acid-base land here is the word neutralized. It's pretty much the only place I can think of the entire year where we use that word. Now in 64, you're asked about write the name of the laboratory procedure used. When we have an acid and a base neutralizing one another, it is a titration. For 65, show a numerical setup again. Notice we're not calculating an answer for the molarity of the HCl solution. Let's find the equation and we'll come back and set it up. On reference table T, here it is, and notice the word titration. If you couldn't remember the word for the other question, you might realize it if you took a look at the reference tables. And here is the equation. Let's go back and plug in our values. I went ahead and wrote down the equation. I like to have my students put the formula for the acid on one side and the formula for the base on the other, then just pull out the numbers here in these couple of sentences, and you end up with the setup. M times 15 is equal to 0.11 times 18.2. That ends part B-2. You got one more part if you've been working on this exam, part C coming up. As always, have fun, good luck, and keep working hard.